Okay, so this is the 14th lecture, and the topic for today is the countability axioms. And for the countability axioms, it is less analysis, so it is less motivated directly from analysis, but it is more focused on topology itself. Okay, so the basic goal from now on is to prove the horizontal metrization theorem. So it basically says that for any x that is second countable and regular, so second countable is some countability axiom, and regular is some separation. It's a separation axiom. Okay, so for any space that satisfies a certain countability axioms and certain separation axioms, then x can be embedded into a metric space, which implies that x is metrizable. Okay, all right, so this is the basic goal, and today's topic is on countability axioms. So recall that when we studying metric spaces, right, we see the notion of first countable spaces. So let's just restate it so that we can remember it better. So for any topological space, if x is a point in x such that there exists a countable neighborhood around x such that for any neighborhood of x there exists a element from the collection such that is entirely contained in U. Okay, so this is basically a local neighborhood system around x, right? So if this works for any point, then x is called a first countable space. And remember the theorem, or these two theorems when we study in metric spaces. So these two theorems, it states that for any topological spaces, there exists a sequence in A such that xn converges to x implies that x is an enclosure of A, and it converts true if x is first countable. And for the continuity, f is continuous implies that for any sequence such that xn converges x, then f of xn converges fx. And the converse is true if f is first countable. Okay, so these theorems are theorems from the metric spaces, right? Okay, all right. And now we give a definition of a second countable space. It's basically a space that has a countable basis. And observe that second countable implies first countable, right? Second countable implies first countable because if you just take the countable basis as our local neighborhood system at any point, right? So we'll just derive it right now. So suppose we have, okay, so if it's countable, so if x has a basis, Bn, right? Countable basis of x, countable basis of x, then for x and any neighborhood U of x. Okay, so for any neighborhood U of x, then exists a basis element, right? Exists a basis element such that x is in Bn and Bn is contained entirely in U. So yeah, like if we already has a countable basis, then this collection is a local neighborhood for any point. It works for any point, right? So yeah, second countable implies first countable. Exactly. Okay. All right. And example is that R is second countable, right? If we just consider AB with AB both rationals, set up all such open intervals. It is indeed a basis for x. Okay, I mean for R. Okay. The reason why is that the basis of the rational intervals and the collection of all real intervals, right? They generated the same topology, so that's what we're saying. You can verify it by yourself, but in fact, R is second countable. And we have a theorem for first and second countable spaces. So this is the central part for our theorem. So given any second countable space, A is a subspace of X, then A is also second countable. And for any collection of second countable spaces, then the product space, product topology, remember, not box, is second countable. And the same as first countable. So if we replace second by first, right? It's the same thing. It follows the same thing. Okay, so let's just prove the first one. And the first one is pretty easy. For any B countable basis, then the collection of them intersect A is a countable basis for A. Right? Is a basis for A because by theorem, right? This is by a theorem, right? If it's a basis for X, then all the elements intersect with A serve as a basis for the subspace topology on A. And this space is a countable set because B is countable, right? So this can identify with any B intersect A, we can just map it to B, right? So this is really a bijection, so yeah, it's a countable set. And motivated by this, right, we can attack on this. Okay, so let's do this. Okay, so let Bn be a countable basis for Xn. Okay, so Bn is a countable basis for each space Xn. So the elements look like this, where I is the running index. Then the collection of the product of U and I's, right? It's the product of U and I's, such that the UIN are the basis element for finally many n, and all others is equal to the entire space. So by the knowledge of product topology, this is the basis for Xn, right? So here's the theorem from product topology. So suppose each X alpha has a basis B alpha, then all of the product B alpha is the basis for box topology. If it's such that only finally of them, the rest of all equal to X, is a basis for this in the product topology. Right, so this is the theorem. And the proof is already given, right? The proof is already given. So really, this collection is really a basis, right, for the product topology. And now the hard part is to show that this collection is really a countable set, right? So like you may stop and think about it. How do we prove that this set is actually a countable set, right? So like I was thinking, like when I trying to verify it by myself, right, we know that each U, like if it's like only finally many n is in the Bn and all other is the entire space, for the finitely many, it can really just view as a finite Cartesian product of countable sets, right? So okay, so here's the proof of showing that it is countable. So we let Ln be the pre-image. So this is the projection map, or the pre-image of projection map onto nth coordinate. So yeah, is basically the collection of all pre-image of UIN for UIN and Bn. Right, so this works is precisely for the space Xn, right? We have the Ln is the pre-image of the projection on all the U and I's, where U and I's and the Bn, right? We have this, right? We just take the pre-image of all of them, and then we form a set. Okay, so each of them. So for example, if n equals to 1, then L1 will equal to U1 1 times x2 times blah 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 collection, and U1 2 times x2 times x3 times blah 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 blah, and U1 3 times blah blah blah, and so on, right? So this is L1, right? So make just kind of picture the set in your mind, and we let KJ. Okay, the set KJ is a set of all intersection of Sn where Sn and Ln. So where n runs through the index set j. Okay, so let's just work it with slowly. So it is an intersection of SNs where n runs through an index set j. Okay, and each Sn is an element from Ln. Okay, each element from Ln, where j is a finite subset of the natural numbers. Okay, so this really just, right, for each j fixed, right, right, if we fix in j, we have a collection of those type of intersections, right? For j is finite subset this. And for all such finite j, the kj, we take the union is really the basis for the product topology, right? Like pause and think about it, right? Okay, so we have this. Okay, now we have this. Each Sn, right, intersection of Sn where Sn, we take the intersection where n runs through the j's, where j is a finite subset of for each j. Right? This all such j. We take a union. And we take a union of all such j. Well, this really gives us B, the basis for the product topology. And obviously each element is countable, right? Each of them we can identify with u and I, right? We can have a bijection. So this is countable. And for j being fixed, so I just want to discuss each j independently. So we fix the j. Kj, right? Kj can be viewed as a finite product of Ln's, right? For example, if j is equal to 1, 2, 3, right? If j is equal to 1, 2, 3, right? Then think about how would kj look like. How would k of 1, 2, 3 looks like, right? It will be an intersection of S1, like S1 intersect S2 intersect S3, where S1 is an element like this, S2 is an element like this, and S3 is an element like this with 1, 2, and 3, right? And this will really just look like some U1, 2 times U2, 7 times U3, 100 times x4 times x5 times blah, 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 and so on. But these first three, right, is a finite product of elements. All such set, right? So each kj can be viewed as a finite product of elements, right? Finite product of countable sets is countable. So each kj is countable. So for j fixed, kj is a countable set. Okay, now we'll continue. We want to show that the set of all such j is countable. If we have the collection of all finite subset of n is countable, then we have a countable union of countable sets, which is countable, right? So we want to show that all such j is countable. And to show this, we let im, so suppose that you have m elements, right? So for each j subset of n, j have m elements, that is finite. For each j, right, like with m elements, right, j can be viewed as an element of this, of the n product of n. So again, suppose like m is equal to 5, right? So we have elements of like 1, 5, 7, 99, 700, right? Then this can be viewed as 1, 5, 7, 99, 700, like, right, is an element of this, right? 5, right? So it's n times n times n times n times n, right? So if you have m elements, if each J has m elements, it can be viewed as an element of this, right? So this is really can be viewed as a subset of this. So IM is kind of a subset of this set. Kind of like it can be embedded as a subset of this, right? So this is again countable, right? IM is again countable, right? In fact, like this is way larger than IM, right? Because each IM is a set, right? And we arrange it into a Cartesian product, which is a subset of this, right? So, like for example, if m is equal to 3, right? 1, 2, 3 is same as 2, 3, 1, right? But they can all be arranged into 1, 2, 3, which is subset of contain n times n times n, right? Yeah, okay, so that's what I'm saying. And if m runs through all the n's, right, all such IM is a countable union of countable sets. So this is countable, right? And this precisely describes all the case. So again, this is a countable union of countable sets, so B is countable. Okay, so this is the hard part of this lecture, right? Just count all the countable sets. And for 3, if we just swap to our veil point to first countable spaces, now it works out similarly, right? For x, we verify the subspace thing first. Well, for x and a, of course we're in x, so we pick a neighborhood, countable neighborhood around x. Then we intersect with a is a countable neighborhood of x and a, right? As desired, right? And for any sequence xn and each bn, right? For each xn, right, we have bn have a countable neighborhood for xn, right? And B is equal to exactly the same collection, right? Exactly the same collection. Instead for countable, before is a countable basis for xn, right? Now we just countable neighborhood for little xn, and we take all such product. Of course, it's countable. Like we already talked about this, right? And it is a local neighborhood around x. This is what we want to verify. It's a local neighborhood around x. So for any W that is open in the product topology, such that it contains x, then by the definition of product topology, x is contained in some basis element that is contained in W, where the basis element, each Vn is neighborhood of x, right? And for n such that it is not equal to the entire space, there's only finally such n, right? For n such that Vn is not equal to the entire space, we have the local neighborhood back here, right? We have a local neighborhood such that xn, un, vn, right? And I would just take the product, the result follows, right? The rest follows. Right. And the first countable just follows similarly from second countable. Okay, so here's a definition of a subset that would be dense in a space. Is that the closure of A is equal to X. Okay, so this, like combine from above, right? Combine as in the very beginning. If X is first countable, right? If X is first countable, then any elements, if X is an A, if this is equal to X, right? If A is dense in X, so suppose A is at X and X is first countable, then any point in X has a sequence that converges to X, and the sequence is in A, right? So this is what we mean by dense, right? For any in the big space, there exists a sequence from a small subset, such that the Xn converges to X. Okay. So this is the one interesting thing about the set being dense in the space. Okay, and this you can think about it similarly, right? But this is nothing work with the closure, but okay. Okay, and the theorem states that if x is second countable, then we have that for any open cover of x, there exists a subcollection such that it is countable and it still covers x. And second, we have that there exists a countable subset of x such that it is dense in x. Okay, second countable implies a countable subset that is dense in x. Okay, let's just prove A first. Okay, so the proof of A. Now first, we give a countable basis of x. And we fix an countable basis of x, okay? Let's just prove part A first. For any open cover x, right? For any open cover x, what we're going to do, we're going to define the set Sn. It consists all the elements from the open cover such that it contains Bn. So this n is here. Sn is all the elements A and A such that it contains Bn. It contains Bn. So Sn is all the A such that it contains Bn. Okay? And let J be the n such that Sn is non-empty. Let J be the subset, which is a countable set. Right? It could be finite, it could be infinite, right? But it is a countable set. Right? And you might ask, what if J is empty? In fact, J cannot be empty, right? So suppose, let's just prove it here as a side note. If J is empty, right, then none of Bn in any A, right? But we know that A is an open cover of x, right? So if we fix x naught in x, we know that x naught is in some A, right? Then by the definition, there exists Bn such that x naught contain Bn in A. So for this n, Sn is not empty, right? So yeah, J is, right, which contradict our assumption. None of Bn is in any A, but here we just find a Bn that is in some A, right? So yeah, J cannot be empty. J is non-empty, okay? So it could either be finite or countably infinite, right? It's a subset of the natural numbers. Okay, now, the central part of this proof is that by axiom of choice, right, there exists a choice function from J to union of Sn where n runs through J, such that Sn is an Sn for all n and J. Which means that, this means that for each Sn, we can pick an element A, right? We can pick an element in Sn. So this is what we call by axiom of choice, right? Choose an An, right? And we denote An as the Fn. So we did consider the collection of Ans, where n runs to J. Well, it is countable, and to see that it covers X, for any X, we can pick A such that X contains A. And we can pick a Bn such that X is in Bn that is a subset of A. Right? So this n is in J. This n is in J means that Bn is contained in An. So S is contained in An. Done. Right? X of n and J such that X is in An. Right? This is the crucial part. Right? If n is in J, then Sn is not empty. Right? So this set is not empty for this n. So there's this set is not empty. Right? And by axial choice, we can, for this AN, right, is contains Bn. Okay, so yeah, second countable implies this. And also part B, if D is a countable subset of X, then the closure of D is equal to X. Well, we'll just let I be the n such that Bn is non-empty, right? For each Bn is non-empty, we pick a point. And we'll let D be the collection of all such points where n is in I, right? Then the closure of this D is equal to X. Why? Because for X and X, any basis contains X. For any basis Bn contains X, this Bn must be non-empty, right? So Xn is in Bn, and Xn is also in D, right? We're picking Bn. So for this n, right, we have an Xn that is in Bn. And by the definition of D, right, Xn is also inside D, which means that any basis contains X, Bn intersect D is non-empty, right? Which means that X is in the closure of D, which means that D is dense in X. Yes, so this is everything for the countability axioms. And next time we're going to walk through the separation axioms, okay? So I'll see you guys next time.